Welcome! I am delighted to introduce our presentation, Zig Algorithms, the Art of Zero-Cost Abstraction. Today, we will explore a curated showcase highlighting the power of the Zig programming language, specifically focusing on Comptime Generics, Explicit Allocators, and SIMD optimization. Based on the Top Alg collection, this session aims to demonstrate how Zig achieves high performance through these unique features, while maintaining absolute control over hardware resources. Let us begin our deep dive into these fundamental concepts.
Zig reimagines standard algorithms by removing hidden control flow and leveraging compile-time logic to fundamentally shift the performance and safety calculus. Our first key advantage is comp time evaluation. This feature allows us to generate lookup tables and unroll loops before the program even runs. By shifting this computational work to the compilation phase, we achieve the significant benefit of zero runtime overhead. Next is explicit memory management. Zig provides fine-grained allocator control with absolutely no hidden allocations. This transparency ensures that memory behavior is always intentional and visible, leading to highly predictable performance across your applications. Finally, Zig emphasizes hardware sympathy. With native support for built-in SIMD vectors and packed structs, the language is designed to align perfectly with the underlying machine architecture. This synergy results in superior cache optimization, allowing developers to extract maximum efficiency from modern hardware.
Implementing a generic binary search often presents significant performance and safety challenges. In many standard languages, generics incur runtime overhead through vtables and dynamic dispatch. This lack of strict type validation can lead to unexpected runtime errors, while the use of function pointers for custom comparisons often blocks the compiler from performing essential inlining. Zig's approach leverages Comptime Generics to provide a truly zero-cost abstraction. By resolving types at compile time, validation errors are caught during the build process rather than at execution. This allows the compiler to generate specialized code where comparators are fully inlined, removing the overhead of function pointers entirely. A critical feature of this approach is the use of optional return types. By utilizing the question-T syntax, Zig replaces the need for sentinel values, such as -1. This forces developers to explicitly handle not-found cases, leading to safer, more expressive code that prevents common logic errors. Moving to the next topic, let's examine graph traversal and the utility of arena allocators. The primary challenge with graph algorithms like BFS and DFS is that they generate frequent, small, temporary allocations. In many languages, this results in memory fragmentation and requires complex cleanup logic. Zig addresses this through arena allocators. This approach provides explicit control, letting the caller define the memory strategy. One of the most significant benefits is batch deallocation, where a single dia-init call frees all nodes instantly. Additionally, the bump pointer mechanics optimize performance by eliminating fragmentation entirely. The key insight here is that for graphs with sizes known at compile time, Zig's flexibility allows for zero heap allocation entirely, further streamlining your application's resource usage. Moving to our third section, we examine the integration of dynamic programming with Comptime and SIMD. The first major optimization is Comptime memoization. By pre-calculating lookup tables during the compilation phase, we can transform expensive recursive or iterative processes into simple O(1) runtime lookups, effectively shifting the computational burden away from the execution stage. The second optimization is SIMD parallelism. This involves utilizing hardware vectorization to compute multiple subproblems simultaneously. A prime example is the calculation of prefix sums for the max subarray problem, where parallelizing the workload significantly accelerates performance on modern processors. By implementing these techniques, we achieve remarkable efficiency gains, resulting in O(1) space complexity for Fibonacci calculations and reducing the space complexity of the longest common subsequence algorithm to O(min of m, n). In Section 4, we examine sorting and hardware sympathy. The central challenge with traditional scalar sorting algorithms is that they frequently suffer from performance bottlenecks caused by cache misses and branch miss predictions. Zig addresses these issues with a three-pronged solution. First, it utilizes SIMD sorting networks to provide branchless sorting for small arrays, achieving 4 to 8 times the throughput of scalar methods. Second, it employs cache-friendly blocks to minimize data movement and reduce cache misses. Third, it leverages Comptime unrolling to fully unroll loops for small arrays at compile time, removing overhead. The key insight is the effectiveness of hybrid strategies. By embedding SIMD networks to handle small subarrays within a larger quicksort implementation, Zig achieves a highly optimized balance between high-level algorithmic efficiency and low-level hardware performance. String matching presents a classic engineering challenge. Naive search methods are too slow, while more efficient alternatives often demand excessive memory. Our implementation in Zig utilizes the BitTap algorithm to overcome these limitations. By leveraging native bit manipulation operations such as popcount, CTZ, and CLZ, we achieve high-level parallelism, processing up to 64 pattern characters per cycle. Performance is further optimized through the use of packed structs, measuring just 18 bytes, which significantly improves cache locality. Furthermore, we utilize Zig's unique Comptime features to calculate Knuth-Morris-Pratt's failure functions during compilation, entirely removing the computational cost of preprocessing from the runtime execution. To understand where Zig fits within the modern programming ecosystem, let's examine the comparative landscape across several critical features. First, regarding generics without overhead, Zig leverages its Comptime mechanism to provide zero-cost abstractions. This matches the performance of C++ templates while avoiding the runtime overhead found in languages that rely on empty interfaces. In the realm of compile-time validation, Zig offers robust native support. This stands in contrast to the more limited application of concepts in C++, while providing the same level of rigorous checking found in Rust's trait system. When handling optional returns, Zig utilizes a built-in optional type syntax, denoted as $T. This approach provides the safety of Rust's option type, but represents a significant improvement over the use of sentinel values, which are common in older systems languages and frequently lead to runtime errors. Furthermore, Zig allows for inline comparators via Comptime functions, a level of optimization that is difficult to achieve in other languages without increasing code complexity. The central takeaway is that Zig successfully bridges the gap between different paradigms. It achieves the safety guarantees of Rust and the high-performance capabilities of C++, yet it avoids the inherent complexity of both by maintaining a simpler, more streamlined language design. When analyzing complexity and optimization, it is essential to see how modern language features can enhance classic algorithmic performance. Starting with binary search, which maintains a constant O of 1 space complexity, Zig utilizes Comptime Generics to provide robust type safety without introducing runtime overhead. In graph traversals like BFS and DFS, where time complexity is O of V plus E, Zig's arena allocators drastically improve memory velocity by handling batches of allocations efficiently, thereby reducing the overhead associated with standard memory management. For the longest common subsequence problem, which traditionally requires O of mn space, we can leverage SIMD and space optimization techniques in Zig to reduce that footprint to O of min of mn, significantly improving cache performance. While quicksort remains O of n log n, the implementation of SIMD networks allows for a substantial constant factor reduction, maximizing hardware throughput. Finally, the O of m preprocessing cost for the Knuth-Morris-Pratt algorithm can be shifted entirely to compile time using Zig's Comptime feature, resulting in zero runtime cost for the preprocessing phase and immediate execution of the search.
Robustness and edge cases are critical because an algorithm is only as reliable as its handling of worst-case scenarios. In our approach, empty inputs, overflows, and single elements are treated as first-class citizens within the test suite to ensure comprehensive coverage. We manage empty and single inputs through explicit logic to maintain stability. Overflows are proactively prevented by utilizing mid-calculation checks. To handle instances where a result is not found, we enforce type handling via optional types. Lastly, we include specific detection logic to identify graph cycles, which is essential for the integrity of topological sorts.
This slide illustrates our development methodology, which is centered on the red-green refactor cycle. This process begins with the red phase, where we write a failing test to define a specific new behavior. We then proceed to the green phase, implementing the minimal amount of code required to make that test pass. Finally, the refactor phase allows us to clean up and optimize the code for better maintainability, without altering its functionality. To maintain clarity across our project history, we follow a specific commit convention. We use feat to denote new behaviors, fix for defect corrections, refactor for structural improvements, and perf for changes that enhance performance. This combination of iterative development and standardized documentation ensures both high code quality and clear team communication. Zig is fundamentally changing how we approach systems programming by allowing us to develop algorithms that are significantly safer, faster, and clearer. By leveraging robust compile time validation, we can ensure code reliability long before execution. Performance is pushed to the limit through the native use of SIMD and the unique Comptime mechanism, which executes code during the compilation phase for maximum efficiency. Furthermore, Zig's commitment to no hidden control flow makes the logic transparent and easy to reason about. To see these benefits in practice, you can explore the full codebase and performance benchmarks within the top_alg repository.